Hi, in this video we are going to talk about the heap implementation, and as we have discussed earlier, it is just a simple binary search tree with the heaps property. So let's get started. I'm going to create a package with heaps, for example. I'm going to have a heap, and I'm going to have a a class app. Okay, and let's get started with the heap. It's going to be class, so I'm going to create like this. It's going to have a static variable heap size. It's going to be 10, for example, whatever you want. We are going to have a initializer constructor, and it's going to self.heap equal to 0. We are going to store integers, so we have to allocate the memory as much as the heap size. So it is going to be an array of integers, and we represent the heap as an array, as we have discussed earlier. And we are going to have a field variable current position. It is equal to -1 in the beginning. Okay, we are going to have a method insert. Of course, we have a data we want to insert into our heap, or let me call it item, because they usually call it as item. Okay, first of all, we have to check whether the is our heap is full, and if it is full, then we print that the heap is full, and we just return. And else we just have to increment the current position, self.current position +1, and we just have to insert at the current position, self.current position, we have to insert the item. I think it's pretty straightforward. Okay, and it's very important that we have to fix up, as we have discussed in the theoretical video. We have to fix up, keep fixing our heap, because the parent may be greater than the children, and sometimes we have to make swaps accordingly. So that's why that's fix up method, we have to implement it. Self.current position. I'm going to have an isFull method. It's going to get a self, okay, and if the self.current position is equal to the heap size, that means that our heap is full, so we return true, else we return false. Okay. The next method we are going to implement is the fix up method. Def fix up. So we have to keep comparing the items, the parents and its children's, and we have to make swaps accordingly in order to maintain the heap property. So we have a parent index. Parent index is equal to the integer we just have to cast, or integer, and I think the fix up method is going to get an index, yeah. So we have to index -1 divided by 2, and it's always get the index of our parent. As we have discussed, I think we have talked about it in the theoretical video, that how to calculate the children with the help of the parents index. and reverse. So while the parent index is greater or equal than 0, and self that heap that parent index is less than the self that heap that index, we just have to make the swaps, and we just checking until it scores the parent index must be greater than 0. We just keep comparing the parents with the childs, and if the parent is less than the child, because it's the parent index, it means we have to make the swaps. So temporary variable, it is just a basic swap. So with the index, okay, the self that heap that index is equal to the self that heap that parent index, the self that heap that parent index is equal to the temp. The index, we have to change the indexes, of course, in order to be able to iterate through. Is equal to the parent index, and we have to set the parent index to the next parent. So integer index divided by 2, index minus 1 divided by 2. Yes, I'm not sure. I think we don't need this brackets. Okay, so that's all about the fix up method. Sorry. We are going to have a get maximum. A get maximum. It's going to have, it is just the result. As we said earlier, in a max heap, the maximum element is at the heap with 0 index. It is the root. So the self that current position is equal to self that current position minus 1 self that heap on the 0 index is equal to the self that heap that self that current position. We just swap the indexes. We have to remove the obsolete references, so we have to deal the self that heap that self that current position plus 1, and self that fix down, we have to fix down with 0 and minus 1. I'm going to talk about it later. And we have to return the result, of course. We have to fix down because in this case we start at the leaves and we keep comparing the upper parents. But the fix down method, we start at the root and keep maintaining the heap's property accordingly. I mean, we keep getting down. Okay. So we have the fix down method. I'm going to talk about the fix down and the heap sort implementation in the next video because it would take too much time. Thanks for watching.